Hello students, welcome to the next session of Raspberry Pi, an embedded Linux programming course. This is the projects module. Here we aim to build a simple, digital camera. Let's take some pictures and video with the Raspberry Pi camera module and Python code. This is where we currently are. So in this session, first we define the scope of the project. Next, we list out the requirements and features of the project. And finally, we draw a block diagram of the project. So let's begin. Scope. The scope of the project is defined as follows. Interface the standard version of Raspberry Pi camera module to Raspberry Pi 4 BSBC. And develop the source code and schematic for implementing a digital camera with preview, snapshot, video recording, and video streaming capabilities. Project requirements. A digital camera with preview, snapshot, video recording, and video streaming capability. This is our general requirement. The specifics are as follows. First one is, the preview window should have OSD menu and time display. Use push buttons to navigate the menu. Play beep sound on button press. Another requirement is to capture a snapshot on pressing a push button. When snapshot is captured, play camera shutter click sound. The third requirement is as follows. Start or stop video recording on pressing a push button. Play beep sound on button press. Blink a LED until the recording stops. Similarly, start or stop the recording of time-lapse video on pressing a push button. Play beep sound on button press. Blink a LED until the recording stops. Another specific requirement is video streaming. A simple MJPEG video streaming server should also start on camera initialization. Now let's take a look at the block diagram. A simple block diagram depicting what we plan to do is shown here. Several versions of Raspberry Pi camera modules are available, such as the 5 megapixel type, which is version 1.3, the 8 megapixel version, which is camera module 2, and the 12 megapixel version, which is camera module 3. The version we are going to use is version 1.3. It features a 5 megapixel OV5647 CMOS image sensor. The maximum image resolution supported by this sensor is 2592 by 1944 pixels. The sensor also supports 1080p video at 30 fps, 720p video at 60 fps and 640 by 480p video at 60 or 90 fps. The recommended best resolution is 1080p or Full HD resolution. The sensor has a fixed focus lens on board. It is enclosed within the plastic package of the sensor module. The camera module PCB is connected to Raspberry Pi using a 15-pin ribbon cable to the dedicated 15-pin MIPI camera serial interface or CSI connector on the SBC. The CSI connector was designed especially for interfacing image sensors. The CSI bus is capable of carrying extremely high pixel data rates. Connect and configure. Connecting the module. To connect the sensor PCB to the SBC, first locate the camera module CSI connector on the PCB. Lift the plastic clip to loosen the connector. Then insert the ribbon cable into the connector. Make sure the contacts on the ribbon cable are facing the contacts inside the connector. After that, tighten the clip by pushing it. The other end of the ribbon cable comes attached to the sensor PCB. If it's not, the same procedure has to be done at the sensor PCB connector also. Enable the camera in Raspberry Pi. We are doing this project on Raspberry Pi 4 BSBC. The OS version used in this evaluation kit is Bookworm. The OS version before Bookworm was Bullseye. Since the Bullseye OS version, support for camera is enabled by default. So tools for dealing with camera modules are already available in the file system, as shown here. In earlier OS versions, this wasn't the case. You had to enable the support for camera using the Raspi config table. RPiCam apps. The camera tools before the Bookworm OS version were named libcamera tools. The Bookworm version renamed them to RPiCam apps. Raspberry Pi comes pre-installed with RPiCam apps that can be used to control the camera module. We discussed them here. There are mainly 5 basic RPiCam tools. Let's check them. RPiCam Hello. On running this tool, a camera preview stream is opened and displayed on the screen. This is good for testing and previewing the scene. RPiCam JPEG. This tool runs a preview window, then captures and saves high-resolution still images as JPEG. RPiCam Still. Earlier OS versions used a camera tool known as Raspi Still for capturing images. RPiCam Still emulates many of the features of the original Raspi Still application. RPiCam Vid. This tool captures video and saves it as H.264 files. RPiCam RAW. The sensor used in the camera module is a Bayer sensor. So if you need to capture the raw and processed Bayer frames directly from the sensor, this application can be used. Now let's try these tools one by one. First, let's try RPiCam Hello. RPiCam Hello displays a preview window of the camera video feed for 5 seconds. After that, it closes by itself. To run indefinitely, use the following command. A timeout value of 0 runs the preview indefinitely. To scale the window size and fix the origin, use the preview option. 100, 100 are the XY coordinates of the origin of the window. 640 is the width, and 480 is the height. The option N can be used to suppress the preview window. RPiCam Hello can also be used to print certain information regarding the sensor. The option Info Text is used for that. The option N can be used to suppress the preview. %frame indicates the frame number. %FPS indicates the frames per second of the current preview. %EXP indicates the exposure value applied in the sensor. %AG indicates the analog gain value applied in the sensor. %DG indicates the digital gain value applied in the sensor. %RG indicates the red pixel gain, and %BG indicates blue pixel gain. Now let's try RPiCam JPEG. First, let's save a JPEG image using RPiCam JPEG. Now let's scale the picture and do the same. The preview timeout is also reduced to 2 seconds. Moving on to raspberrypicam still. This utility can be used to save JPEG images just like raspberrypicam JPEG. Its another use is to capture the image in various formats such as PNG, JPEG, BMP, YUV, and RGB. For YUV and RGB formats, the application that reads these files should know the binary data order in these files. Let's try raspberrypicam with next. Let's capture video now. Use the following command to record the video as H.264 encoded files. You can also specify the frame rate, the width, and height of the video. To play the recorded video, use VLC player. Finally, let's try the raspberrypicam raw tool. raspberrypicam raw records video as raw bare frames directly from the sensor. Let's record a 2-second frame. You will need bare converter application to display this file. There are a few more controls and features available with these command line tools. We shall look at them when we start doing the project. Hello students. Welcome to the next session of Raspberry Pi and Embedded Linux Programming course. This is the projects module. Here we aim to build a simple digital camera. Let's take some pictures and videos with the Raspberry Pi camera module and Python code. This is where we currently are. This is module 4, and we are having the Python controls session from topic 1. This session aims to introduce how to use Python code to control the Raspberry Pi camera module. Let's take a look at the objectives of this session. So in this session, first we introduce the picamera library package that enables us to use Python for controlling the camera module. Next, we learn a few basic methods such as rotation, text overlay, and resolution change. And finally, we use Python to do a few image tuning settings such as brightness, contrast, saturation, and so on. So let's begin. Picamera library. The picamera library can be used to capture images and videos, and also to customize the settings of the picamera. To check if picamera is installed, use these commands. The commands fail, indicating that picamera is not installed. Let's install it. That also fails, which means this has to do something with the OS version. For OS versions before Bullseye, picamera is the package version to be used. For OS versions from Bullseye and later, you have to use the picamera 2 library instead. So let's install picamera 2. The picamera 2 is already pre-installed in Bullseye OS. So let's try a few basic operations. Preview. Let's open a preview window using Python code. We would be able to see the live images from the sensor using a preview window. First, we import the picamera 2 class from the picamera module. We are going to use that class to get access to the physical camera. We also import the preview class. Then we create an object from the picamera class. When we create this object, the camera will start initializing itself. It requires some time to do it. Possibly 2 seconds. Generate a camera configuration suitable for preview. Configure the camera system with that preview configuration. Start the preview window. And then start the camera running. Now wait for 5 seconds. After that, stop the camera. And then stop the preview. If you don't want the preview, but start the camera system, you should use the null preview argument. If you want the preview to run indefinitely, do not stop the camera and preview. Also wait indefinitely in an infinite loop. Capture. Let's capture an image using Python code. Use the following line to capture and save the image. Provide the path of the destination as required. Record. Now let's record a video using Python code. To record a video means capturing multiple frames. Use the following line to record a video for a duration of 5 seconds. So now we have covered the basics of how to use the picamera 2 library. Let's move on to some advanced settings now. Rotation, text overlay and resolution. First, let's see how to change resolution. In our previous exercise we did with picamera 2 library, you may have noticed that the resolution is 640 by 480. Let's change it. Let's begin with the preview window. Use the following command to change the window resolution and window start point. The last argument, that is the transform argument, is used to flip the image horizontally or vertically. Doing both flips causes the image to invert. That is 180 degrees rotation. It's also possible to maintain the current view. To use the transform, import the transform library. We shall see all this one by one. Now you saw that the preview window was reduced to the size 320 by 240 as specified, and the transforms worked. But the captured image resolution is still 640 by 480. How to change the resolution of the snapshot or the recorded video? For that we have to create a separate record stream. So now we have two streams. One stream for the preview and the other for record. Change the record or main stream resolution and record it. To change the main stream resolution, use the following commands. Here the main size is the resolution to be used for recording and is set as Full HD. The low resolution is set as 320 by 240. Also we have set the preview window to use the low resolution and the encode routines to use the main size. Let's try this. You can change the resolution up to the maximum resolution for still image capture. But for video, the resolution should not go beyond Full HD. You might have noticed that the transform parameter is happening only on the preview window. It's not happening on the encode stream. How to do that? Also, how do you set the FPS of a video recording? First, let's apply FPS. Do the following change in create_video_configuration statement. Set the controls value and apply the frame duration limits. For 25 FPS, it is 40 milliseconds. So set 40,000. Now we have to resample this video file using the FFmpeg tool and convert it to MP4 file. Use the following statement for that. Now if you want to encode the transformed scene, use the transforms in create_video_configuration as shown here. For capturing the transformed still image, use the following statement. Now let's see how to do text overlay. Let's add some text on the image as well as on the video. Let's see how to put date and time on the image. We require OpenCV package for this. First, let's install OpenCV. Use the following command to install. After installation, check the version. Let's put date and time overlay on both low-resolution preview display as well as on the main encode stream. We shall record a 10-second video of resolution 1920 by 1080p at 25 fps to test this. So most of the code related to video and its recording remain the same. We shall see the additional code needed for overlay. First, we have to import the OpenCV package we just installed. We have to import the mapped array module also from picamera 2 package. This mapped array module is required to gain access to the capture buffers. To this image capture buffers, the text overlay data is added. For that, let's create a new function. In this function, first we obtain time in a human-readable format using strftime. Then we overlay this time data onto the mainstream image buffer as well as preview stream image buffer using the put text routine from OpenCV library. The position of the text, the font to be used, the text color to be used, the thickness and scale of the text to be used, all can be specified as arguments to this function. We want this overlay to be applied for each frame captured. For that, this function has to be specified as callback to the picamera 2 object. So that completes the discussion on code. Let's try this now. Image tuning. Now we move on to some image tuning exercises. Several image tuning parameters are available for the camera module. A detailed list can be found in the picamera 2 reference manual from the following link. We explore some commonly used tuning methods here. We try to enable or disable auto exposure, set exposure time, set analog gain, set brightness, set contrast, set saturation, and set sharpness. All these tuning can be applied in the create_video_ configuration or create_still_ configuration as you require. A sample implementation is shown here. Let's go through the settings one by one. The auto exposure can be enabled or disabled by setting it as true or false. Let's put it as false and see what happens. The image is dark. Now since auto exposure has been disabled, we have to set the exposure value and the analog gain for a reasonably bright image. Let's do it. The exposure is set in terms of microseconds. Let's set the value as 30,000 microseconds or 30 milliseconds. The image is still not bright. We have to increase the analog gain value. Let's put it as 10. Now the image is reasonably good. Let's change the brightness settings now. 0.0 is the default brightness. 1.0 is too bright, and -1.0 is dark. Let's try this. Moving on to contrast, the value can be changed from 0.0 to 32.0. Let's check it. Similarly, the saturation value can be changed from 0.0 to 32.0. 0.0 results in grayscale image. Let's try that also. Finally, we move on to sharpness. The value ranges from 0.0 to 16.0. Let's try that next. The image will get sharper as you increase the value. We wind up our discussion on image tuning here. I would suggest you to explore OpenCV libraries also. It is a very useful image processing library, used in various applications, including machine learning and AI. A digital camera with preview, snapshot, video recording, and video streaming capability. This is our general requirement. A simple block diagram depicting what we plan to do is shown here. The specifics are as follows. One of them is, the preview window should have OSD menu and time display. Use push buttons to navigate the menu. Play beep sound on button press. Another one is, capture a snapshot on pressing a push button. When snapshot is captured, play camera shutter click sound. Start or stop recording videos on pressing a push button. Also play beep sound on button press. Blink a LED until the recording stops. Similarly, start or stop time-lapse video recording on pressing a push button. Play beep sound on button press. Also blink a LED until the recording stops. The camera also needs a streamer as part of its requirement. A simple MJPEG video streaming server should start on camera initialization. These are the specifics of the camera project. For doing this, we require the following hardware: a Raspberry Pi SBC, a camera module, 4 push buttons, a LED, and a speaker. Now let's move on to draw the wiring diagram. Wiring diagram. As shown here, we have connected the push buttons to GPIO pins. Also, the LED for indication has been added to GPIO 6. A speaker has been connected to the audio output connector of the Raspberry Pi. The rest of the wiring is self-explainable. You can see the actual setup here. I have soldered the push buttons to a Vero board for easily wiring it to the Raspberry Pi using hookup wires. I am using a USB-powered speaker. The USB cable for powering the speaker is connected to the USB connector of Raspberry Pi. The audio stereo cable from the speaker is connected to the audio output of the Raspberry Pi SBC. Flow diagram. Let's move on to the software flow diagram. The camera gets initialized in still capture configuration at a maximum resolution of 5 megapixels. Also, a preview window with a resolution of 640 by 480 is opened. The preview window will have text overlay of date and time, as well as the menu button for editing the settings. MJPEG streamer is also initialized at this point. The MJPEG streamer will be streaming the preview window frames at 640 by 480 resolution. The camera is initialized with 0-degree rotation, auto exposure enabled, 25 frames per second, and default values for brightness, contrast, saturation, and sharpness as shown here. The camera starts running, and if the capture button is pressed, the image is saved. On clicking the menu button, the settings page is opened. The cursor button can be used to move the cursor to the required setting, and the edit button can be used to edit the setting. Pressing the menu or OK button exits the menu page. The settings available in the menu are as follows. Switch to photo mode or video mode or time-lapse mode. The switch to photo mode setting configures the camera in photo mode. In photo mode or time-lapse mode, the main resolution can be 2592 by 1944 pixels or Full HD or 720p. The switch to video setting configures the camera in video mode. In video mode, the main resolution can be Full HD, 720p or 640 by 480. For video, the max resolution allowed is Full HD. The rotation menu rotates the image by 0, 90, 180 or 270 degrees. Auto exposure can be enabled or disabled as true or false in the menu. The manual exposure can be set from 1 microsecond to 30 milliseconds. The analog gain values can be set from 1 to 10. The brightness values range from -1.0 to 1.0. Likewise, the contrast values range from 0.0 to 32.0. Saturation can also be set from 0.0 to 32.0. Whereas sharpness ranges from 0.0 to 16.0. And finally, the record duration can be set from 1 second to 60 seconds. To reduce the complexity of the project, only minimal menu settings have been used in this project. Source code. Let's move on to write the source code. This is a very long source code. The final source code is given for your reference. Also, to help you understand, we will move in a step-by-step manner. We have split the source code in the same step-by-step manner, and that is also available for download. Practically, it's difficult to explain a source code, token by token. It is expected from the learner to learn from the code, and use the given code and explanation as references. We create a Python source file camera.py for implementing the source code. The basic code framework is as follows. Here the main function is shown invoking three functions, for initializing the LED, the buttons, and the camera module respectively. The main function pauses its execution after that. The rest of the camera activity happens in the background. We shall populate the functions shown here, and also add a few more functions and supporting variables implementing the camera functionality. First, let's complete the LED initialization function. First, we import the LED module from GPIO0 library, and initialize it by specifying the GPIO number, which is 6 here. A global variable is used as handler for the LED module, connected to GPIO6. Next, we complete the button initialization function. For that, we import the button module from GPIO0 library. Then specify the GPIO pin numbers, to which the buttons are connected. We also specify the debounce time as 50 milliseconds, to filter out false button presses. We have 4 push buttons. One for moving the cursor, one for editing the value, one for entering or exiting the menu display, and one for capturing an image or record a video. We use global variables as handlers for these buttons. For each button we assign a callback function, which will be invoked when the button has been pressed. So now we have added 4 new functions which we shall populate later. Next, let's see how the camera module is configured. If you remember, we have 3 modes for the camera as per the project requirement. One is snapshot mode, the second one is video mode, and the third one is time-lapse mode. Snapshot and time-lapse mode are basically the same. In both the modes, the image or snapshot is captured. The maximum resolution is 5 megapixels or 2592 by 1944 pixels in both these modes. In snapshot mode, when the capture button is pressed, only one image will be captured and saved. Whereas in time-lapse mode, images will be captured and saved at intervals of half a second or 500 milliseconds for the specified duration of time-lapse recording. However, in video mode, the video recording of specified duration will be saved as MP4 file. The maximum resolution is Full HD or 1920 by 1080 in video mode. There are specific routines in the picamera 2 library for initializing the camera module in image capturing mode or video capturing mode. But before that, we have to initialize the picamera 2 library. For using the picamera 2 library, import picamera 2 preview and mapped array modules from picamera 2 library. Then we have to assign a callback function to the picamera 2 library. This callback routine would enable us to modify the image buffer array and also change the image settings dynamically. We will discuss about this function later. We then initialize the rotation variables using apply rotation function. We shall see this one also later. Create _ video _ configuration is used to configure the camera module in video mode. Whereas, create _ still _ configuration is used to configure the camera module in image capture mode. The decision to use which mode depends on the value of the global variable capture _ mode. This variable can be 0, 1, or 2, depending on user's choice. If it is 0 or 2, then it's image capture mode. If it is 1, then video capture mode is used. Within these functions, image tuning settings such as auto exposure enable, exposure value, brightness, contrast, saturation, sharpness, etc. are also applied. Similarly, the transform routines apply the amount of rotation required for the image. For using the transform routines, import transform from libcamera. We can fix all these settings to specific values or use variables so that they may be modified dynamically. We have used global variables here. The values from these global variables will be used for these image settings. These variables can be modified using the menu and edit buttons according to the user choice. For video mode, the frame rate can also be applied. We have fixed the preview window to be of low resolution at 640 by 480 pixels. The main resolution will be used for capturing the video or image. Finally, we apply the camera configuration just created, start the camera preview window, and enable the piopensource system as shown here. Now let's see the apply rotation function. Depending on the user's choice of degree of rotation, we flip the image horizontally or vertically, or maybe both. Global variables are used for this. These global variables are used in the transform routine of camera module configuration. Now let's populate a few button callback functions. First we see menu button. The menu button toggles the menu display. Global variables are used to do this. The cursor button moves the highlight on a menu item. The cursor button works only if menu is enabled. There are 11 menu items. The first item can be any one from the switch_mode list. The rest of the items are shown in the menu list. Let's populate the edit button next. The edit button can be used to change the mode in which the camera module is configured. Change the rotation of the image frame. Or maybe, change the main resolution. Change the brightness, contrast, saturation, and sharpness of the image. Enable or disable auto exposure, manually set the exposure and analog gain, and also, change the recording duration. All these settings can be changed and applied dynamically. Let's see how this is done. We use global variables for each of these settings. To edit a setting, use the cursor button to move to that menu setting, and then press edit button to change it. To change the camera mode, the current camera system has to be stopped first. Then the camera has to be configured by calling the configuration function. The same applies to changing image resolution also. The current camera system has to be stopped first. Then the camera has to be configured by calling the configuration function. Remember that video and image resolutions are different. We have created two separate lists for image and video resolutions to choose from, as you can see here. For rotation, the rotation variable is edited. Depending on the value, the appropriate string from the rotation_menu list will be shown. The apply rotation function we saw earlier will use the value of the rotation variable to rotate the image from the main resolution stream. This main stream is used for capturing and saving. The preview window image will not be rotated. The rotation of the preview window is a bit different and complicated. We shall see that later. For the rest of the settings, corresponding global variables are edited. At the end of the function, pycam2 controls is used to apply the made changes immediately. We move on to the capture button now. Depending on the selected mode, the button triggers for an image capture, or a video capture, or a time-lapse capture. First, we have to create a timestamp using strftime function. We will be storing the videos under vid directory, the snapshots under img directory, and the time-lapse capture under tl directory. For video capture, first a temporary H.264 file will be recorded. Then this file will be converted to MP4. Using the timestamps, file identifiers, and the path required, we create the name of the target file. Then using the pycamera 2 library functions, the image or video is captured and saved. The project requirement stated that shutter sound should be played for image capture, and beep sound should be played for video capture. For that, I have downloaded appropriate sounds from freesound.org in WAV format. To play the sound, use the play application. Invoke the application using subprocess call. We haven't discussed the apply OSD overlay function yet. Let's do that now. This function does a few things that needs to be done in every frame. That include text overlay on preview as well as main resolution, preview image rotation, save preview frame as JPEG for MJPEG streaming, menu display, and finally, highlighting of menu item. Let's see them one by one. The current time has to be displayed on the main stream. This is the only activity done for mainstream in this function. It is done on the mainstream image buffer mapped array. Apart from this, all other activities in this function happen on preview stream. The preview resolution buffer has to be manipulated for a few things before presenting for display. First, it has to be rotated depending on the rotation setting. The rotation of preview stream is complicated. The preview frame is in YUV420 format. This has to be split using array slicing. Then the flipping can be done on individual channels for rotating the preview frame. Second, the text overlay has to be placed. For the preview stream, the camera name, the current camera mode, the current resolution and timestamp has to be displayed. These text data will be placed towards the bottom of the preview stream. A transparent overlay will also be provided to highlight it. Thirdly, the preview image frame has to be saved as JPEG files for MJPEG streaming. It will be saved in MJPEG folder. Finally, the menu has to be drawn if the menu button has been pressed. The overlay for the selected menu item also has to be drawn, depending on the cursor position. So that completes the camera.py source code. Now let's move on to the MJPEG streamer source code. What is an MJPEG streamer, and how do we create one? Suppose our camera is installed in a remote place, or maybe in an elevated position out of reach. How would you see its live frame? In such cases, it's best to create a streamer, streaming the frames one by one. For that, we need to create a server socket. Our server socket will be serving JPEG images. So if a user wants to see the live view from our camera, he can do so by connecting to our server. Our server will start sending JPEG frames one by one over socket connection. This is what a streamer does. Since it's JPEG frame being streamed, this server is called MJPEG or Motion JPEG Streamer. Let's proceed to make one. We already saw how to make a server in an earlier session. We do the same here, but in Python language. So we create another Python source file mjpeg.py for writing the MJPEG streamer code. We have to create a server socket, listening on a specific port number first. For that we have to import the socket module, for using the socket routines. Then create a socket object using the socket routine. Next we bind this socket object to a port number we require. Here we choose the port number as 8080. Once the binding is successful, the socket is ready to listen for connections from other computers. So next, we put the server socket in listen mode. The server is listening now for connection requests from other servers. The server can accept connections now. But it can't serve any data now, as we haven't done that part. Let's do it. We know that the server is going to serve JPEG frames. Where is this JPEG frame coming from? From apply OSD overlay routine in the camera.py code, we saved the preview frames at 640 by 480 resolution as JPEG files to the MJPEG folder. This frame or file will be served in the MJPEG streamer. When a connection request is accepted, HTML responses will be first written to the socket. Then the contents of the file will be read and written to the socket. There is a specific order in which these HTML responses and JPEG content are to be written. Follow the source code to know that. Once the frame has been sent, the file inside the MJPEG folder will be deleted. That will allow the next preview frame to be saved inside the folder. And this process continues until the connection is stopped by the client. So how does the user connect to the server? The user can connect to our server using the following URL: http:// followed by the IP address of the Raspberry Pi followed by a colon, and then the server port number. In my setup, it will be http://192.168.149.121:8080. Where would you use this URL? Open a browser in your computer and type this link in the browser. Or you can open VLC Media Player and then play network stream by providing this link. Make sure that the user's computer and the Raspberry Pi are on the same network. That's it. We have completed the source code. Let's see how to run it. We have two Python source files. We will be running both files separately. To automate the process, we simply put the commands to run these files in a script as shown here and run the script. That's all about the source code. Scope of testing. The scope of the testing is defined here. Run the camera code and verify the following. Did the camera boot up in image capture mode at 5 megapixel resolution? Is a timestamp running as text overlay on preview window at 640 by 480 resolution? Is the LED blinking on button press? Does shutter click sound and beep sound play on capture button press? Is snapshot capture working at all resolutions? Is video capture working at all resolutions? Is text overlay working on captured image or video? Does image rotation work on preview as well as capture? Does settings change get applied dynamically? Are MJPEG streaming and time-lapse mode recording working? Testing. Let's test the features. The results are shown in this video. Project summary. So finally, let's conclude this project with some observations. Our project was a success. We were able to implement all the project requirements stated in the proposal. However, there is still scope for improvement. We list a few improvements and additions here. The current MJPEG streamer can serve only one client at a time. Rewrite the code to serve multiple clients concurrently. Implement user authentication to view streams over network. Implement user authentication to enter camera settings menu. Implement a web server for the camera. Implement RTSP streaming protocol for H.264. Implement more camera settings to take full control of the image quality. For example, white balance settings, dual exposure, etc. Make use of the mapped array buffers for advanced image manipulations. Use OpenCV to do post-processing on the captured image. Implement object detection and face detection. Try other camera modules with better sensitivity. Use V4L2 drivers if picamera 2 doesn't support them. So that brings us to the end of this session. We tested the prototype we created. We tested all software implementation of camera functionality. We also discussed the improvements that could be done to the project. For a detailed reference on Raspberry Pi camera software modules, please refer the following link. The takeaway from this session should be a clear understanding on the positive outcomes, as well as shortcomings of this project, that should definitely help in your future project works. We have a final test next. See you there. Thank you.